Section 10.4 is having us work with applications of quadratic equations, or we can think of this as story problems with quadratic equations. That's recommended before we get going on a lot of these problems that, as necessary, go back and take a look at all of our methods for factoring quadratic equations from Chapter 7, extraction of roots from 10.1, and its two forms that we had, our method for completing the square, and how to use the quadratic formula. All of these are going to be very, very helpful as we go through and solve these story problems, and some of them actually have some nice little questions we can ask ourselves to determine if we are going to use one of these methods compared to the other, depending on the problem that we are working with. You do want to know how to work with all of them because there are some times where completing the square might be more effective or factoring might be more effective. Maybe in other cases, the quadratic formula is going to work best for you. It just depends on the nature of the problem that we have been given. Last part I do want to note about our methods that we do have here. I would recommend that you know that all of these methods will work. Some will be a bit more efficient and go a bit faster than others. And I would also advise an immense amount of caution with only defaulting to using the quadratic formula from 10.3. It's a very, very nice method. It's very effective in that it will pretty much always get us our answer. However, it only works in one very, very specific scenario, which is everything in standard form, and it can result in numbers getting particularly larger and maybe a little bit painful to work with. So there's nothing wrong with it, but be open and be flexible to any of our other options depending on what we are presented in the problem. Now, before we dive into some actual problems that we're going to see here, and we do have several that we're going to take a look at down below, I would invite you to think of some possible strategies as you are going through these story problems. This is something that I find regardless of whether this is an Algebra 2 class like we're taking a look at, or maybe it's a calculus class, maybe it's pre-algebra, or maybe it's just basic number counting, 1 plus 1 equals 2 sort of stuff. I recommend that we take some time to read and reread problems as much as we need to. A lot of people really skip that, and we just try and read the problem once and think, okay, great, I've read it once, now I know exactly what to do. And I don't think that's entirely fair to you, the person who's learning this material, because it's an unfair expectation for yourself to say, great, I should be able to read it once and make full sense of it, which I don't think is always possible. A lot of these problems get very complicated, so I think rereading these things a minimum of 3 times is perfectly reasonable. And if you need to read it more than that, go for it. I don't think there's anything wrong with that at all. I would also recommend that we try and think of these problems as puzzles. Within that, all of these puzzles have provided you all of the necessary information that you need to actually go through and solve it. Doesn't necessarily mean that's going to automatically make it any easier, but all the information that we do need is there, or we're going to assume it's there. We do have the occasional poorly worded problem, or a teacher or instructor makes an error in how they've written something, but we're going to assume that those are very much exception cases and assume that everything is there and given to us. So as necessary, when you are reading through those, again, these two kind of go hand in hand, all the information has to be there, and I'll reread it as much as I need to. Just because all the information is there does not mean the problem is going to make that information very easily understood. So this might mean that you need to dig into what you've been reading or that paragraph of stuff and really take some time to just noodle on what the problem is saying that you are doing, or the information that it is presenting to you. Again, no need to rush it in this regard. The last thing I would make a note of is, as we are trying to fuse the ideas that we have here of reading multiple times and thinking of these things as puzzles, I would recommend that we try and also get into the mindset of looking at all story problems in 2 parts. The setup part and the actual solving part. I like to refer to this second part as doing math. So if you want to think of it like that, you're welcome to do that as well. Now, it should be noted, I'm going to rip off the Band-Aid here and state that there unfortunately is no way, no one single method to solve all story problems. So you are going to need to develop and practice some different strategies. Maybe we'll see a few of them in the examples here today. Maybe you'll see some in other videos online like a Khan Academy or other ones that you find on YouTube, and maybe you try some of those. I think some very useful things that are worth noting are making some bullet points for yourself. Maybe we're underlining parts of problems. I tend to find creating and writing pictures out with labeling included into those pictures tends to work very well. And you can also do something like create a variable library, which is a fancy way of stating, hey, this is the variable x that I'm going to use. What does this variable x represent? Hey, I'm going to use the variable y. What does the variable y represent? It's only after we've gone through all of the setup portion of that story problem, we're trying to get all the information out there, we're trying to make full sense and make sure we understand what is going on, that we then start actually making some equations for ourselves. And once we have those equations, then we can actually start doing math and solving these things. And if you're thinking on that and keeping that in your head as we're going through these examples and noticing, wow, I feel like I'm spending an immense amount of time going through the setup portion, and I'm not doing nearly as much time in the actual solving portions of these problems. That's where we're using our formulas and our processes up here. You would be correct in that. The setup is the part that takes longer. I think it is the more challenging one, and I don't think there's anything wrong with taking longer to make sense of and set up this problem, so it is easier to work with and solve at the very end. So keep those things in mind as we are going through and taking a look at some of these story problems we have here. Let's dive into those. Our first example that we have here is asking us to find two consecutive even numbers whose product is 528. So, all right, let's think on this thing first and foremost. I am told that I have the product of something. Okay, so that means I'm going to be multiplying somewhere inside here. So what we can do, I'm going to set up for myself a set of parentheses. I'm going to have two things multiplying. I don't know what they are, but I'm going to have two things multiplying, and two parentheses next to each other like this does imply that multiplication is taking place. I'm told that the product is 528. That is a buzzword that tells us I'm going to have an equals sign showing up. So two things multiplying equal 528. Now I don't know what these things are, but I can assume that they're multiplying together and they're going to be 528 based on what I've been told. At this point in time, we could start with noting the two things I'm multiplying together. Are they the exact same thing? We're told to find two consecutive even numbers. So based on that, no, I'm going to have two very different things showing up with us. So if you wanted to, for the time being, we could say we're going to have a number x and a number y showing up. And that's going to multiply together and give me 528. Now in this current form that it's written in, I can at least see that I have two things multiplying together and they equal 528. However, the limitation that I'm currently at is I have one single equation and I have two unknowns, two variables showing up in here. With that said, this thing is impossible to solve just as it's written right now, which means that I'm going to need to go through and refine this thing a little bit more. And that's okay, we have the general idea of what we have here. We'll refine it in a step here, a step here, a step here, and so forth, if we need to. Let's go off to the side here and let's just get an idea of what would two consecutive even numbers look like. Let's think on that. Well, if we had the number 2, the next consecutive even number would have to be 4. If I had, let's say, I don't know, 12, the next one would be 14. I'm noticing a pattern that I'm already doing, so I'm going to break that a little bit here. Let's say we had the number 28. Next one that'd be even would be 30. Now let's think on this. What's the pattern that's showing up to go from our first number to our second number? Well, it's the next even one. Okay, so I'm starting with 2, getting to there. If I start with some number, let's say that number is x, how would I find the next even number from that? Well, what are we noticing between these two numbers here in our patterns of even numbers, consecutive even numbers? The second number is 2 more than the first one. So whatever this first number is, we'll call it x now, the next consecutive even number is going to be whatever x is plus 2. And suddenly, I now have a way of finding what this next consecutive even number is using my first one, meaning I can rewrite my original equation to be in terms of one single variable. And now that I only have one variable that's showing up here, I'm doing different things with it in different parentheses, but I still have one single variable. I can now go through and I can solve this thing using any method that I need to find what x is. And once I have x, I can then find what the x plus 2 value is, our first even number and our next consecutive even number. It should be noted that while this here says next consecutive even number, this process that we have in this specific little rule that we have, x and then x plus 2, this will apply if this was the word odd instead. So if we were told to find the next consecutive or 2 consecutive odd numbers, we would still be using the same method that we have here, x and x plus 2. If we were told to find 3 or 4 or 5 consecutive odd or even numbers, we'd have x, x plus 2, x plus 4, x plus 6, and so on and so forth. We're just continuously adding 2 onto the end over here as our numbers are getting bigger. But that's more of a generalized pattern that we can see. Bringing it back to our problem that we have here, now I'm going to go through and actually try and solve this thing. I'm looking at this and I'm saying, right now, I don't think there's any of our previous methods that work in this form. So I'm going to go ahead and multiply this x through, and I'm just going to rewrite this whole thing into standard form. Everything on one side equaling 0. Now that I have everything in this standard form, I can go through and then try and figure out, okay, what's some different ways that I could find the answer to this? What's one way I could find x, and then maybe another way I could find x from here? So from our previous page, we did note that factoring is not a terrible option. We want to see what are some numbers that I might be able to factor this thing into. And I will say off the top of my head, nothing is jumping out at me. This 528 is a pretty big number, and I do not know the factor pairs that multiply together to create that. So it is an option, but it could take a while. Our second option that we had on our first page was noting that we could use extraction of roots. However, this thing is not written in one of the two forms that is listed there on that first page, so we're not going to use that. It's going to be too much of a pain to rewrite it and go through that process. Completing the square, not terrible. The coefficients aren't bad, but I don't think it's going to be particularly nice here. So in this case, we're going to end up using the quadratic formula. So as necessary, identify what your a, b, and c values are. I think it's very nice to write those out for yourself. So we got 1 for our a value, 2 for b, and negative 528 for c. Remember that it's always the number and the sign that's in front of it that goes for our a, b, and c values. And now I'm going to plug this thing into our quadratic formula. If I can scroll this thing up a bit, there it goes. If you need to, rewrite the quadratic formula for yourself. And then we're plugging in the numbers that we have for a, b, and c in for a, b, and c in this equation that we have right here. And we're going to solve this thing out. I will note that as you are going through and writing this thing out and solving it, make sure you are always substituting inside of sets of parentheses. It takes missing that once and a stray negative sign showing up, and then this whole thing could very well fall apart, which we don't want. At this point in time, I am now at the point where I have the instance of needing to determine if I'm working with the positive and the negative, so I need to split this thing into two parts. One instance where I'm adding 46, and an instance where I'm subtracting 46. I'm going to move us up and do that right here. Split this thing in half. And continue on finding my answers from here. Now from here, we're looking at this and we're seeing, okay, I have x is 22 and I have x is negative 24. These two numbers are, they're kind of consecutive. This one's a 22, this one's a 24. But the problem is one of these is positive and the other one is negative. These things are not consecutive from one another. So I have two potential x values that I could be using here. Remember that we need to find two consecutive numbers, so whatever my x value is, I need to find the next one that comes after it by adding 2 to that. So as I'm scrolling back down here, for my first x value of x is 22, what would the one that comes after that be? Well, that would be a positive 24 because it's 22 and plus 2, which would give me 24. So my first possible set of numbers are, whoops, got a small pen there. Let's use this one. 22 and 24. What would our other ones be? Well, I have negative 24. If I add 2 to that, I would also get a negative 22. So in this problem, I technically have two sets of answers. An instance where 2 of them are positive, and an instance where 2 of them are negative. If we think on this in the context of multiplying numbers together, 2 negatives would make a positive, and 2 positives would also make a positive. So be on the lookout for that. Just because we have two answers that are opposite signs doesn't necessarily mean we can't have two sets of answers as the final answer to that problem. Zoom this out here so we can hopefully see a little bit of an overview of all of this. There we go. There's example 1. Our second example is as follows right here. Deadpool's going to jump and attempt a superhero landing from the top of a building. His trajectory can best be described with the equation y equals negative the quantity t minus 1 squared plus 80, where y is height in feet and t is time in seconds. After how many seconds will Deadpool land on the ground? Round your answer to 2 decimal places. We have a lot going on with this. Again, these aren't always exactly the easiest and most straightforward problems with what's going on and what am I solving for and how do I get to it. So we're told something about his height here. We've got a little bit of information alluding to two variables that we have here, y and t. Y represents his height in feet and t represents his time in seconds. The problem is asking us, after how many seconds will Deadpool land on the ground? So I'm going to be looking for and should expect to find a t value at the very end. T equals something. I'm also trying to figure out, okay, when he's landing on the ground, well, why is his height in feet? Would it make sense to have ground or the ground level be something like 10 feet or 50 feet or 100 feet? What exactly makes sense with that? So if we're told that he's landing on the ground, that tells us that my height, in this case y, is going to be 0. What's nice about that, as I'm looking at my equation, I have two variables originally, y and t. With this revelation of landing on the ground, telling us that y is 0, I suddenly have an equation where all I have is one single variable. I have 0 equals negative t minus 1 squared plus 80. And now I can just solve for this single t that's right here. It's one variable, and now we can use all of our methods at our disposal with this. Again, I'm looking back on a separate screen here at our different possibilities. Could I factor this thing? Well, not exactly, because I have this t minus 1 all being raised to the second power, and I have this 80 at the end, and then I need to multiply a negative. That just seems like a lot of work. Let's not do that. Looking at our second option, extraction of roots. This equation that I'm looking at right now looks very similar to the second possible equation that we have showing up with the extraction of roots. And I invite you to go back and take a look at that if necessary. But looking at it, this right side of this equation is looking very similar to that, so I'm going to say let's go ahead and use extraction of roots to go through and solve this thing. So I'm going to go ahead and jump to doing that using the same process that we learned back from 10.1 to solve this equation and get our t value. And from here, I now get the instance where I have my time, t, is equal to 1 plus or minus the square root of 80. Like we did with our previous problem, I need to work with the instance where I'm adding the square root of 80 and the instance where I'm subtracting the square root of 80. So I'm going to move us back up here and then show splitting that into our two possibilities and finding our answers from there. And once again, like our previous problem, we're noticing I have two answers showing up. Well, let's think on what t represents. In the context of this problem, we were told that t is time in seconds. So does it make sense to have a negative time for this problem? Not really, because we're moving forward in time. We don't yet have the time Infinity Stone. That's in a separate series of movies. So we can't exactly work with that negative time here for our final answer. We would have to use a time of 9.94 seconds as our final answer here. And that would be our final answer for example number 2. For our third problem, we are told Junkrat is attempting to launch himself over a 45-foot tall wall. After some number crunching, he determines the equation of his trajectory over time as h of t equals negative 16t squared plus 80t, where h of t is height in feet and t is time in seconds. Will Junkrat be able to launch himself over the 45-foot wall? So this is really a yes or no question. Will he or won't he? And we can think too, what kind of a shape are we going to be getting out of this? Well, maybe a little drawing here might be helpful. So I'm just going to do that right below here. So if we have Junkrat, say he's standing right here, he's going to be launching himself something about like this, and we're trying to see if he's going to be able to make it over a wall that is 45 feet tall. Something about like this. And will he basically reach the height that he needs to of 45 feet to go over this wall? We can safely assume that if he reaches this 45-foot mark, he's probably going to go over it, as the problem has kind of included within that. So let's keep in mind here what we're looking for, what we're at, and what we're solving for. So we're really wondering, is he actually going to be able to reach this height at all? So with my problem, I've been told h of t is height in feet. Fantastic. And I've been told t is time in seconds. So we need to determine if there is any time or times that he will actually reach this height. And we've been given what that height is. So we can rewrite our original problem with the substituted 45-foot height in at the very beginning. So I should be getting 45 equals negative 16t squared plus 80t. And at this point in time, now we go back through our options that we had on that first page and say, all right, which one or which ones are going to work best for us here? I'm looking at this and I'm really not seeing where factoring is going to be possible, even if we move this 45 over to the other side by subtracting 45 on both sides. I can't really factor anything particularly easily with this, so I think I'm going to have to use the quadratic formula because this isn't an extraction of roots form either, and completing the square, yeah, I've got really big coefficients showing up here. I don't really want to deal with that if I can avoid it. So I'm going to go do what I did with the first problem, which was I'm going to use the quadratic formula to go through and find my 1 or 2 or potential t values for this thing. Like we did with our previous problems, we have the instance where we are adding the square root and then subtracting the square root. So I'm moving us up and splitting that apart again for our 2 potential answers that we could get here. And here we are finding that we have 2 times that are showing up. One of the first time here is t is 0.66, and the second time is 4.35. Look back up on our problem and we're noticing that t represents time in seconds. So is he going to reach this 45-foot height? Yes, it turns out he is actually going to hit that in 2 spots. Sometime, maybe somewhere over here on our little picture, and then sometime over here on our little picture. So he's actually going to reach 45 feet, go above that, and then come back down to 45 feet. But are we asked what that exact time is? No, we're not. Are we asked what is his height or what's his maximum height that he gets with any of it? We're not asked about that. We're just asked, will he be able to launch himself over that 45-foot wall? And we can safely conclude, based on what we just calculated here, that yes, he absolutely can. looking at our final example here, we are told two military planes take off at the same time from a military installation. One flies west and the other flies north. The plane traveling west is traveling 100 miles per hour faster than the other plane. After 30 minutes, radars indicate the two planes are 250 miles apart from each other. What is the speed of each plane? So I feel like this is one of the ones, as I was alluding to at the very beginning of the video, where we have a lot of things going on, and yeah, we've got things going in different directions, we've got different speeds, we've got times, we've got distances. I don't think it's clear and obvious at all what we're supposed to do with this thing. So let's start with maybe drawing a little bit of a picture with this. I like to think of this as channeling your inner Bob Ross with these sorts of problems. It should also be noted that this is for a math class. It's not for an art class. You don't need to be, perfect at your drawings with these. They don't need to be pristine, though adding in some detail can always be fun. Okay, so we have one plane that's traveling north here. We have one plane that's traveling west here. Okay, we're told the plane traveling west is traveling 100 miles per hour faster than the other plane. So I've drawn this just to show I've got a little bit of a longer distance here. I don't know what that exact distance is, but it should be longer because it's been traveling at a faster speed. The one going north is a bit shorter there. Now, I've also been told after 30 minutes, radars indicate the two airplanes are 250 miles apart from each other. So that tells me that the distance between them, I'm going to use a dotted line here for this, or a dashed line, that distance there is going to be 250 miles. Now, if we're looking at this thing, what are we noticing? Well, we've kind of made a triangle here with this. And we're working with distances, and we have a particular formula that helps us work with the distances of a triangle, and that's going to be the Pythagorean theorem. Quick reminder on that, Pythagorean theorem is the formula a squared plus b squared equals c squared. A and b are the two legs that make the 90-degree angle, and c is always the hypotenuse. So in this case, the 250 miles. However, at this current time, I do not know what the distance traveled of each of these planes currently is. The best I can do is refer back to our distance rate time equation to say, what's the distance that the plane traveling north has gone? Well, that distance is equal to some speed or some rate. I'm going to use rate here for the sake of the fact that my S's and 5's look really similar, so I'm going to use R for rate. It's that rate, some amount miles per hour, times 30 minutes. I'm working with hours for speed, so I can write in for my time 0.5, because 30 minutes is half of an hour. For my other plane, the rate that it's traveling is whatever the north one is, which is R, plus 100 miles per hour. Again, we go back to the plane traveling west is traveling 100 miles per hour faster than the other planes. That's where I get R plus 100. It's the slower plane's rate, plus 100 miles per hour. And how long is it traveling for? It's also traveling for 30 minutes. We're told these planes take off at the same time, and then later on we're told after 30 minutes. That tells us a more exact time they've been traveling. So now, I still might not know these exact rates or distances that these things have traveled, but I now have all of this and all of this in terms of a single variable, R. Could do a slight rewrite with these and make this first one 0.5 R, and the other one is going to be 0.5 R plus 50, just distributing this 0.5 through to everything inside here. So, theoretically, my first distance is 0.5 R plus 50. My other distance is 0.5 R. And I can plug both of these in for A and B in my equation, and this 250 in for C. We'll just go ahead and do that quick rewrite here. So 0.5 R plus 50 to the second power plus 0.5 R to the second power equals 250 to the second power. Now from here, noticing, okay, I've got one single equation. with one single variable in it, so I can actually go through and expand this thing out and rewrite it and see what I get on both sides of this equation. So I'm going to go ahead and expand and multiply things together and simplify that down before I determine which method I'm going to use exactly to solve for my final answer. And at this stage here, I'm looking at this going, yeah, these numbers are kind of big and they're gross and they're terrible. I'm going to try getting everything over onto one side, getting this thing into standard form. I'm going to do a little bit of modification with this 0.5 out front because I don't like a decimal or a fraction showing up here. And then I think I'm probably going to end up having to use the quadratic formula because some of these other numbers just look way too big and not exactly great to work with. So that's what I'm going to do here. I'm going to get everything equal to 0. I'm going to do a little bit of a rewrite to scale all of these coefficients or these numbers up to get rid of this 0.5 specifically, and then I'm going to use the quadratic formula to get to my potential answers. There we go. So now I'm looking at this thing, and that looks like it's a much more manageable standard form quadratic equation. This C value here at the very end, very big number, doesn't exactly look like it's the most fun to work with, so yep, we're going to use the quadratic formula because all of our other methods aren't going to exactly be the easiest thing to use when I have a big number here. So I'm going to continue on with that to get to our final answer. Now from here, we're noticing that yet again we're getting two answers, two different speeds for the planes. Remember, R also corresponds with the northward plane we have on display here. So would it make sense for us to have a speed of 300 or a speed of negative 400? Well, we can't really have a negative speed in the context of this problem, so we can pretty much just eliminate that and forget about it there. So the speed of our first plane is going to end up being this 300 that we have right here. Now we do have to figure out what's the speed of our second plane, and our problem has told us that that second speed is r plus 100. So 300 plus 100, that's going to give us 400 miles per hour for our second problem, or our second plane, I should say. So wrapping things up with a quick reminder what we covered with the 10.4 material. we have our 4 primary methods at our disposal to go through and solve these things. There is rarely, if ever, one method that is always going to work better than the other ones. Quadratic formula is probably the most common one that a lot of people want to go to, but as we saw with some examples, try some of these other ones just to see if they may or may not be available to you. Sometimes they'll work better and a bit faster, sometimes not. It depends on the nature of the problem and the information that we've been given. And then beyond that, we had just some other things to keep in mind as we're going through story problems. Make sure we are reading those things multiple times. We're thinking of these things as puzzles more than anything else. All the information is there and given to us. We just might need to read it a few times to make sure that we understand what the problem is telling us. And then overall, thinking of these things as mainly the setup portion that we're doing first. I'm drawing my pictures, I'm underlining things, I'm making bullet points as necessary, and then I'm actually going through and solving this thing using the mathematical processes that we've learned and discussed in previous sections. And do not jump to the solving portion until you've done the setup. It does tend to take a bit longer to do the setup, but it is worth it because if we don't have the correct setup, then we're not going to do the correct process, and or even if we do, we potentially find wrong answers doing that. Then we had our 4 problems here, just putting these back on display if anyone would like to look at those again for yourself if necessary. And then our final answers to each of these things right here. But that will do it for the 10.4 material, applications with quadratic equations, or you could think of it as story problems with quadratic equations.